The situation is very similar if you look into the ITC. Just have a look here at the first Josephson junctions made from ITC material. This is a polycrystalline material, and the grain boundaries actually look wonderful as Josephson junction, but not as tunnel junctions. It's also just there quite a strange coupling from either just SNS, superconductor normal and superconductor and the coupling and partially tunneling. This was then quickly culturized in these bicrystal junctions, where you have two crystals with a different orientation. You deposit the film on top and thus get a very nice linear grain boundary, and if you just make some structures on top, you find that this behaves like the Josephson junctions. They are still around and they are dominating the squid market with the superconducting quantum interference device and sensor market. Then very quickly here is very complex multi-layer system by Chow. Conductors came up. And this was really somewhat misleading. People were at that time expecting if you can make so many layers on top of each other, it's already just around the corner that you make complex circuits. What we got is proposals where it was said that you can make a superconducting computer just operated at liquid nitrogen temperature. And it turned out that the quality of these junctions was miserable and the reproducibility also. And this was a real dead end. Maybe also just at the end, somewhat the end of conductors. In IBM, one worked on these steps where IPCO to IPCO connections were down here via a material which was deposited across a step, and grain boundaries were coming up here at this step. So one had a nice coupling for IPCO to IPCO, again, for grain boundaries. Also, one could just put on code. But this wasn't very well developed, and we thought, just at that time, thought, why not just making this angle here very flat to something of the order of 20-25 degrees? Because in that case, you can have epitaxy all through the sandwich. And what you can do then is just put a base electrode, cut very flat for a ramp for the structure, deposit praseodymium-barium copper oxide epitaxially on it. Praseodymium-barium copper oxide is non-superconducting. And here on top, yttrium-barium copper oxide again. That means if you have C-axis orientation, all the superconducting copper oxide plates are horizontal. And then we get direct coupling through. And it turned out that it worked very well. Then, some years later, just the by Char again and Mokli, there was the idea of interface engineered junction. That means don't put on contextual barrier, but destroy the surface with argon ion beam and then deposit the counter electrode and thus recrystallize some of the surface and form a barrier on this one. And there has been a number of very nice publications on this later on. In 1999 was as well in Japan as in Europe a hot topic, because one thought that the reproducibility would become much better. You see here the preparation step with the argon ion beam. Turned out that the reproducibility was very similar to the epitaxial barrier ones. So there must be something else going on. You see here just a TEM section, in this case here from the group in Munich in Germany. It's very difficult to identify where the barrier actually is. So it's not easy to study that system. If you look what's currently going on, from all these junction techniques, polycrystalline junctions are not in use anymore. Bicrystal junctions, as I said, they still dominate the squid market, and I think it will continue. The point is you have only one grain boundary, long grain boundary. It's not good for electronics. because you cannot just make the junctions anywhere you want, but nevertheless the junction technique is very nice. Template junctions, these are junctions where you make use of the fact that on different materials the orientation of the tin-barren copper oxide can change when it grows on top, and then you get again grain boundaries on that. Steppered junctions, somewhat. Nano-bridges are not used. Radiation damaged junctions, I will come to that soon, came up. Ramped up junctions, yes, and planar junctions. At the time, no. Let's revisit what's now going on. Ion damaged junction, you shoot ions onto the surface of the tin-barren copper oxide. And by electron beam lithography, you make an opening in the resist through which you shoot on it. This way, you can make junctions very near to each other and in a nice pattern. The point is, this length is very critical. And it should be of the order, here it's just optimistic, 20 nanometer to 100 nanometer. A factor of 5 less would be good, or even more. And that means you very critically depend on the lithography and on the quality of the electron. Lithography means just this roughness determines very strongly already the current which can be transported through such a structure. The LV characteristic look very nice, just like you would wish all the LV characteristics will apply in for ITC junctions. The ramp junctions, the development was that these material, the barium material was replaced with other materials or doped. And what we found with, for instance, gallium doping is that we could change, that we have different channels for transport through such a barrier. There's a different channel for quasi-particles, meaning single electrons, and for the super current. And the gallium doping just changes the transport characteristic for the single particles, for the electrons, and not for the Cooper pairs. So one has 2 degrees of freedom. One is one changes the doping for the normal resistance, and one changes the barrier thickness for the Cooper pairs. And that is something which actually worked out quite well. And we can just put in a number of layers in meantime, and I think it's 12 layers like that, 12 or 13 layers of technique which we use for integrated circuit, which in principle works well. And it would be perfect if these junctions would be reproducible. This is just a picture for 2001 publication for these interface engineer junctions. And I found this TEM picture very nice because here you seem to see really parts of the barrier, and you can see that this barrier is not homogeneous. This is not specific to the interface engineer junctions. This is also the case for the architectural junctions. It seems that this is just one of the difficulties.